There's a small collection of several Maclaurin series that are quite common and will get used on a regular basis. As such, we're going to discuss those today. The common Maclaurin series come from anything that have a very predictable derivative pattern associated with them. So I would say without a doubt the most common derivative pattern that we're going to see, or the easiest to recognize pattern that we're going to see, is going to be f of x is equal to e raised to the x power. That's because literally any derivative that I take after this is going to be equal to the exact same function. It's going to be e to the x. As a result, any derivative evaluated at 0 for this function is going to be equal to 1. Therefore, the Maclaurin series expansion of e to the x, which is supposed to be the nth derivative of e to the x evaluated at 0 divided by n factorial times x raised to the n power, is simply going to be the following. This will be x to the nth power divided by n factorial. Now if you take a look at the interval of convergence for this, I'll leave this as an exercise for the viewer. The interval of convergence using the ratio test is going to be all real numbers, negative infinity to positive infinity. This also lets us know a couple of cool representations of things. For example, if we plug in x equals 1, we will get that e is equal to the following. 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so forth and so on. So that would be 1 plus 1 plus a half, ignore that comma, plus a sixth plus 1/24, etc. Two others that have very common derivative patterns would be the sine of x as well as the cosine of x. Most suitably, the derivatives of these two functions, derivative of sine of x gives you cosine of x, derivative of cosine of x gives negative sine of x, and derivative of negative sine of x gives the cosine of x. Evaluating any of these at 0 is going to give us the following pattern. Sine of x would be 0, cosine of x would be 1, negative sine of 0 would be 0, and the negative cosine of 0 would be negative 1. So starting with the sine of x, that would be equal to 0 plus 1x plus 0 over 2 factorial, x squared, going over to here, minus 1 over 3 factorial, x cubed, plus 0 over 4 factorial, x to the 4th, plus 1 over 5 factorial, x to the 5th, plus 0 over 6 factorial, x to the 6th, minus 1 over 7 factorial, x to the 7th, and so forth and so on. You'll notice that for the sine of x, we're only dealing with odd powers. This is also due to the fact that the sine is an odd function. Now expressed in a slightly more compact fashion, we'll get the following. You'll notice that this is an alternating series and that the powers are going up 2 at a time. As a result, the Maclaurin series representation of the sine of x takes on the following pattern. We will see negative 1 raised to the nth power divided by 2n plus 1 factorial times x raised to the 2n plus 1 power. So with this in mind, n equals 0 will correspond to the first power, n equals 1 will correspond to the third power, n equals 2 will correspond to the fifth power, and so forth and so on. Now, in order to get the cosine of x, I can either apply the same sort of logic, or I can simply take a derivative of this series to get the cosine. So when I take the derivative of this, multiplying by this power is going to reduce the factorial by one factor. The negative 1 to the nth power will not change. We'll wind up with 2n factorial and x raised to the 2n power. Now, all three of these happen to be related to each other as well. These three things are related to each other in the following sense. Euler's identity is for complex numbers, and it relates e to the x with the sine of x and the cosine of x. If you take e raised to the a plus bi times x power, that is going to be equal to, you know what? We'll save this for the next video.